Welcome to today's Explainer. Right now, we are looking at the absolute most ambitious nuclear fusion experiment in history. It's this massive, multi-decade, totally globe-spanning effort to essentially build a star right here on Earth. Okay, let's dive into this.
So you might be wondering, why spend roughly $20 billion and decades of intense global engineering effort on a nuclear reactor that isn't even designed to put a single watt of electricity onto the grid? I mean, it sounds completely counterintuitive, right? But stick around, because by the end of this explainer, you're going to understand exactly why this mega project in southern France, known as ITER, is literally humanity's most crucial stepping stone to boundless clean energy.
Here's our roadmap for today. First, we'll look at the magic of nuclear fusion. Second, stars versus Earth reactors. Third, geopolitics and site selection. Fourth, massive construction hurdles. And finally, experimental versus commercial. All right, jumping into section 1, the magic of nuclear fusion, overcoming the Coulomb barrier. To really understand ITER, we first have to understand the physics magic trick that powers the sun, which is called quantum tunneling. Normally, two protons violently repel each other because they both have a positive charge. Think of it like trying to force the north poles of two insanely strong magnets together. They just naturally want to push apart. And that's what we call the Coulomb barrier. Even with the massive gravity of the sun, that electromagnetic force is usually strong enough to keep them apart. But because subatomic particles also act kind of like waves, there's this wild probabilistic chance they can actually bypass that barrier. Essentially, some protons in the sun's core randomly teleport across the Coulomb barrier to fuse with another proton. But this relies on pure chance, and something called beta plus decay happening at the exact right microsecond. Honestly, it's wildly inefficient. In fact, a single proton in the sun has to wait an average of 9 billion years to successfully find a partner. But once that 9 billion year wait is finally over, a rapid chain reaction kicks off, called the PP chain. Step 1, the protons fuse. And via that beta plus decay, a proton becomes a neutron, which creates deuterium. Step 2, that deuterium fuses with another proton in mere seconds to create helium-3. And finally, two helium-3 nuclei find each other and fuse into helium-4. But here is the absolute magic of this whole process. If you add up the mass of the starting protons and compare it to that final helium-4 atom, some of the mass is literally missing. It didn't just vanish, though. It was converted into pure energy. And using Einstein's famous E=mc² equation, we can really see the sheer power of this. If you take just a single kilogram of stellar fuel through this fusion chain, you lose about 0.7% of the mass. That is just 7 lost grams. But when you multiply that by the speed of light squared, you get 6.4 times 10 to the 14th joules of energy. To put that into perspective, that's enough energy released from just 7 grams of fuel to power a city the size of Boulder, Colorado, for over a month. Moving right along to section 2, stars versus Earth reactors, from elegance to brute force. Now, the sun has a major advantage over us, and that is sheer scale. Stellar fusion relies on extreme density. The sun's core is 10 times denser than solid lead, and it relies on that 9 billion year wait time, utilizing quantum tunneling. But here on Earth, we obviously don't have billions of years, and we definitely don't have a star's massive gravity to work with. So we have to use absolute brute force. The ITER tokamak uses a heavier, much more fusion-ready fuel mix of deuterium and tritium. And since we can't replicate the sun's density, we just have to make the fuel incredibly, insanely hot. We have to heat the plasma to 150 million Kelvin. That is 10 times hotter than the center of the sun. We heat the protons up so much that they move fast enough to just plow straight through the Coulomb barrier. And to hold plasma that hot, without, vaporizing the entire machine, we have to trap it in this giant donut-shaped cage made of massive magnetic fields.
Which brings us to section 3, geopolitics and site selection, science in the crosshairs of global politics.
Building a machine this staggeringly complex requires incredible global cooperation. ITER was actually born back during the Cold War in 1985, when US President Reagan and Soviet leader Gorbachev agreed to internationally cooperate on fusion for the benefit of all mankind. But the real world of budgets and politics quickly caught up. In 1998, the US actually pulled out entirely after seeing a $10 billion cost estimate, which severely constrained the project before they eventually rejoined years later. Then, in 2003, picking the actual site became a massive diplomatic deadlock. The participating nations were split right down the middle between building it in France or in Japan. Historical sources note this deadlock was heavily influenced by the geopolitics of the time. It's generally agreed the U.S. stood behind Japan's candidacy partly as political retaliation against France opposing the U.S. invasion of Iraq.
Finally, in 2005, a massive compromise was struck. France would host the reactor, but Japan would receive 20% of the highly coveted manufacturing contracts and research staff positions. All right, Section 4, massive construction hurdles, managing extreme environments. And this brilliantly illustrates just how hard it is to build a sun on Earth. So, with the politics finally settled, the actual building began. And the scale of this thing is just staggering. Because ITER is a nuclear site located in southern France, it absolutely has to be able to survive earthquakes. To pull this off, the entire 400,000-ton tokamak complex, which, by the way, is heavier than the Empire State Building, was built resting on top of 493 seismic isolation columns. Each of these structural columns is topped with a specialized rubber and steel bearing that essentially isolates the massive facility from the earth below. This keeps the whole thing perfectly stable, even if the ground is violently shifting during a seismic event. You know, ITER is truly a machine of massive contradictions. On one hand, you're holding plasma at 150 million degrees. But on the other hand, it relies on these giant superconducting magnets to contain that incredibly hot plasma. The toroidal field coils, weighing over 300 tons each, have to be cooled down to minus 269 degrees Celsius. That is literally colder than the dark side of the moon. Then you've got the central solenoid, basically the heartbeat of the reactor, which uses 43 kilometers of cable to generate 15 million amps of electrical current. That creates enough magnetic force to lift an entire aircraft carrier straight out of the water. Just wild. But doing engineering at this immense scale, with all these highly precise components being built in different factories all over the globe, it comes with some pretty severe risks. In late 2022 and 2023, major construction defects were discovered right on site. Massive metal slices of the reactor's core, weighing thousands of tons, had dimensional nonconformities. Basically, their welded joints simply didn't align when they were finally brought together in France. On top of that, microscopic stress corrosion cracking was found in the vital supercooled helium pipes of the thermal shields. Because of these really harsh realities of global manufacturing, assembly had to be completely paused. This resulted in a massive overhaul of the project's timeline, pushing actual deuterium-tritium fusion operations all the way back to the year 2039.
Finally, Section 5. Experimental versus commercial, the truth about ITER's power generation. So, the crucial point is, these timeline delays bring us right back to our opening question. You'll often hear people say that ITER has a target Q factor of 10, meaning it will supposedly produce 10 times more power than it consumes. But that is the scientific Q factor. It just means the engineers put 50 megawatts of thermal heat into the plasma, and the plasma generates 500 megawatts of thermal heat out. What this ignores, however, is the hundreds of megawatts of actual electricity needed to run all those massive vacuum pumps, the supercoolers, and those giant magnets we were just talking about. In reality, the ITER facility requires about 300 megawatts of electricity just to operate at full tilt. If you try to turn its 500 megawatts of thermal heat into electricity using standard steam turbines, it would actually result in a massive net electricity loss. Future plants need an engineering Q factor greater than 1, where the whole facility produces more grid-captured electricity than it consumes to run its own equipment. And that is exactly why we have such a stark contrast between experimental models and commercial goals. ITER is strictly an experimental proving ground. It's only going to run in short plasma pulses. It will pioneer the advanced robotics needed to maintain a highly radioactive core, and it's going to test special lithium blankets to see if we can literally breed our own tritium fuel on site. Basically, it's doing all the grueling scientific groundwork so that tomorrow's reactor, a demonstration power plant known as DEMO, can actually succeed. DEMO will take everything learned from ITER, operate in continuous steady states, maintain a 100% self-sufficient fuel cycle, and finally hook up to steam turbines to generate usable, boundless electricity for the actual power grid. So ITER isn't going to charge your smartphone anytime soon, but it is the largest international scientific collaboration in history, successfully aligning billions of dollars, cutting-edge physics, and really intense global diplomacy. If this incredibly complex $20 billion marvel is essentially just a stepping stone, is this immense level of global cooperation the only way humanity can ever truly learn to harness the power of the stars? It's an absolutely fascinating question, and it's one that the engineers in southern France are working tirelessly to answer every single day. Thank you so much for exploring this incredible mega project with me today.